3, minus 2, minus 1, 0. And let's give them aligned. 1, 2, 3, 4, 5, 6, 7. Why am I stopping at 7? I can only have 16 values, right? Or of course I could have 32, but then I would start at minus 16 and go up to 15, right? And I'm going to start assigning binary values with 0, right? So 0, 0, 0, 0. We're going to need 4 bits, right? Then we move to 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 4, 0, 0, 0, 5, 0, 0, 0, 6, 0, 0, 0, 7. And then I'm going to come around, right? Sorry, what am I doing? Why aren't you correcting me? 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, right? And now I've run out of 3-digit numbers, right? So I have to move to 4. But we're going to go around, right? So 1, 0, 0, 0, 1, 0, 0, 1. This is what we call complement of 2. 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. Right? So so if I have 32 bits, right? I'm going to represent the I'm going to divide the range, which is 2 to the 32 values, into 2 to the 31 are going to be positive, including 0, and the other 2 to the 31 are going to be negative, right? So then how do I know how to represent a negative, a negative value? Right, so it's pretty easy. I add, right, so if I have minus 8, I take the value of 16 minus 8, right? So I'm going to go to the value 2 to the 32, right? And I'm going to subtract, right? So if I want to represent minus 1, right? So if this was a positive number, this would be 15, right? So if I want to represent minus 1, I'm going to do 16 minus 1, which gives me 15, and I'm going to take the value, the binary representation of the positive number 15, and add it there, right? So now, and this is a rule that we can very easily work out for ourselves. What I want to point out is, again, because of the limited number of bits, we're going to have the same kind of anomaly, right? So if I take the number 6, so we only have 4 bits currently, right? Remember, because this limitation is important. And I'm going to add the value 2 to it. What am I going to get? Well, I'm always wrapping around, right? So I'm going to go 2 steps downwards, but as I reach the bottom, I'm going to jump up, right? So I'm going to do 1 step, 2 steps. So 6 plus 2 will result in minus 8, right? 6 plus 3 will result in minus 7, right? If I have, again, 1 minus 6, no, 1 minus 6 will work okay. If I'm going to have, for instance, minus 7 plus 2, I'm going to get 7, right? And so on and so forth. All right? So let's verify that this is true. So again, we're going to work now with signed values. All right? So if I don't use the signed keyword, the unsigned keyword, I'm going to have signed value. So I'm going to say int b equals, and again, 0 x f f f f f f f f. And notice that I don't have to, the simple fact that I said int b, right, is going to work fine, right? So what's the value of b now? So looking here, it corresponds to this, right? This is an f. So if I use only 16 values, only 4 bits, this is an f, and it represents -1, right? So the same is going to happen here. This is -1. So now we're going to say print f, right, b equals, and now we're going to use decimal numbers, d, right? And let's check that this is indeed -1. Forgot a semicolon. And I should use b here, of course. Right? So b is -1. Right? So let's so let's do b plus b. Right? So that's going to be the interesting thing. B plus b. So if b is -1, we expect the result to be -2. Okay? And b plus b equals %b. Right? So b plus b is -2. That's correct. How does that happen? Let's analyze a little bit how does this happen, right? So I'm here, right? And I want to add actually 15. That's what's happening. So I'm going to go and add, because this number represents 15 in base 2, right? So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I fall on -2. Okay? That's why it's so elegant, because the actual addition doesn't care whether the number is unsigned or signed as a complement of 2 encoding. All right? It's the same hardware operation. Whether I look at that number as signed or unsigned, right, the hardware operation will produce the correct result as long as I preserve the encoding, right? The encoding is a matter of convention. It's up to me whether I want to look at 1111 as 15 or as -1. But as long as I'm consistent, I look at the operands in complement of 2, and then I also look at the result as complement of 2, I get a correct result. I look at the operands as unsigned, and I look at the result as unsigned, here I get a correct result, right? Even though the hardware operation is the same. All right? So this is the very interesting thing. So overflow can happen, right? And let's figure out a situation where it does, right? So I'm going to create a new value. And it's always interesting. When it is interesting, when are we going to experience overflow? When we're here, right? So this is 2 to the power minus 2 to the power 31, right? So if I have 4 bits, it's 2 to the power 3, right? But if I would have 32 bits, it's 2 to the power 31 with a minus sign in front, negative, right? So how do I get this number as a hex? Instead of having, right, my my first bit must be a 1, and the remaining bits need to be 0, right? So I'm going to have an 8, which is 1, 0, 0, and then 7 zeros. 1, 2, 3, 4, 5, 6, 7. Right? So this represents 4 bits, 8 bits, and so on. 28 bits, right? And then inside 8, I have 3 0 bits and 1 bit of 1, right? So this represents minus 2 to the power 31. Does that make sense? So we can say here minus 2 to the power 31 as a comment. Okay? So let's see what we get with printf c equals %d, and then c plus c equals %d. And then we want c and c plus c. And would have been good to have that session here as well. Right? So c plus c is 0 instead. Right? Does that make sense? It totally does. Why? Well, let's look at the 4-bit case. Right? I have 1000. So let me go at the bottom. And I have 1000 plus 1000. Right? So I start from the right. So here I have a 0, right? Then 0, then 0, then 1 plus 1 is 1, 0, right? But I only have 4 bits. So this guy goes away. Right? So the same happens with 32 bits. I only have 32. But you know, that number that we have written here, this one, right? When we double it, when we add it to itself, we get a number that can only fit into 33 bits. We don't have 33 bits, so we throw one away. So we throw the largest away. Okay? All right, so now you're going to ask, why 32? Okay, are there any questions so far? Because you're probably... So why 32 bits? Well, it wasn't always 32, right? The registers what's a register? Because I keep saying this name. It's a piece of memory inside the CPU, right? And when I say the CPU, I mean, nowadays people say the CPU and refer to a desktop box, right? No, so there's a chip inside. There's a processor, what they call the i7 or the i5 or the i3, right? That's the processor, and inside it has registers. And registers are very fast memories, and they have a certain number of bits, right? And they can be seen as numbers, and we can perform operations between these numbers, right? So traditionally, these registers have been very expensive. If you look at the history of CPUs, they started with 4 bits. All right. So the first CPU, the first microprocessor, what you would call a microprocessor, had 4 bits, right? Went up to 8, then to 16, then to 32, right? And nowadays it's 64, and the core processor also have some 128-bit registers inside, right? So definitely has become a lot cheaper, and technology has advanced. All right. So it started with 4. It hasn't always been 32, but it stayed at the value of 32 for a very long time. Right. So it with the 386 processor, which appeared in the late 80s, right? So that architecture lasted till Pentium 4, I think, right? So lasted a good 15 years. In that span of time, a lot of software has been developed that sort of relied on an integer having the size 32 bits. And now, even though processors have evolved and have registers of 64-bit, right? On one hand, the range of 32 that 32 bits give us is generally sufficient to represent a number, and also it has to be backward compatible with a lot of old software, right? So it kind of stuck there. So Java has hardwired an integer to be 32 bits. Many other languages did the same, and so did C and C++. Okay. Now, what if we want larger numbers? Well, we have larger ranges available, obviously, because there are such registers inside the processor. So we can go to larger numbers, and I can have what is called a long integer. All right, and you're going to ask me why long integer and not just long integer. So let's do a d, right, equals. And in this one, I can put, instead of 8 f's, I can put 16 f's. And actually, the case doesn't matter. 1, so it becomes quite tedious. 2, 3, 4, and then I'm going to cut and paste, copy and paste. Right? So this is now a long. And you're going to ask me why long and not just long? Well, the int, very long time ago, when we had 8 and 16-bit processors, was not precisely defined. So they said whatever is the most convenient for the compiler implementation, right? And it turned out that for some compilers, the best size of the int was, by the author of that compiler, was seen as 16, right? Some would go to 32. It never went to 8, even though it could have been possible, but it never went to 8. So int has either been 16 or 32 bits. Because of that, at the point when they wanted to have a fixed size for this data type, they said, oh, we're going to make the short int a 16-bit number and the long int a 32-bit number, right? So if I say long int, nowadays is the same as int. At this point, there's no compiler, no C compiler where the int would be 16 bits. Those are gone, right? But so all of them have int. So it's long int and int are synonymous, right? But because of backward compatibility, right, they made the 64-bit integer to be called long int. All right. So we have this, and we can play exactly in the same manner, right? So we can say printf, and now we're going to see a lot larger numbers. So when we have such large numbers, the specifier needs to be long decimal, LD. I can't remember whether just L works. A D plus D equals percentage LD backslash N, and let's do D and D plus D. All right. All right, so it's the wrong specifier. I have to remember where it is. don't want long double. LLD, you found it? Thank you. So actually, I kind of exited the field of C at the time when 64-bit integers were right. So you see again, this is -1, and then if I replace this number with again, so we're going to have 8, 1, 2, 3, 1, 2, 3, 4, 4, 1, 2, 3, 4. We're going to have the same. But see how much larger the 64-bit number is, right? So there's a lot more range there. Okay, nevertheless, it's still limited. Okay, and we can have overflow. Now, it's still possible to work with embedded systems where, because of memory constraints, you want to work with shorter integers. So it's possible to have shortened E equals, and so here we only have 16 bits, so 8000. Okay, and maybe this arithmetic is not that interesting anymore. So let's make it yeah 8000, and do printf E equals percent. And now I'm going to do B. And I'm going to tell you why in a minute. E plus, because the compiler doesn't care. E plus 1 equals percent B. We're going to do E plus 1. E plus 1, and I think we have to say E plus 1 S here. We want the E to be short as well. So how do we say short? C. Okay, short 2. That should work. So I want a short 1, right? So guess what? When I write this constant here, this will have what size? We'll have default size, which is, I want to produce a constant 1 that is only 16 bits. So this cumbersome way would be the way to produce it. And I forgot the backslash n, right? But you can see there the range. Oh, I wanted -1. I'm sorry. I wanted -1. Oh. Yeah, same here. Sorry. So short. Still not. So by the way, short in once I write short or long, the int is redundant. That's why you're not seeing it. But I don't understand why. So it gets the correct value when I do. Why is this an int? Oh, because it's a percent d here. It's an SD. Printf short. Oh, it's H. Okay, let's try HB. Why is it typed in? It's very strange. All right, so now, though it's a lot of conversions, but so we're trying to keep these numbers to be short, and then the result to be short as well. So for some strange reason, the result gets automatically converted to an int. It's not what we want, right? So notice what's happening here, that when I add 1 to this value, when I subtract 1 from this value, this is e minus 1 actually, right? Remember that it's e minus 1. When I subtract 1 from this value, I get this positive number, right? So it's only 16 bits. It's exactly the same principle, right? And then we can also have 8 bits. And what do you think the 8-bit integer is called? Actually, it might work. I haven't tried. It's a character. So I'm going to say character f equals, and actually I'm going to give it a character value. I'm going to give it a character value, which I'm going to I wish I knew what was that, but let's do it. Let's do this \7f, and let's do the same thing. Print f, and I'm gonna do something new here. So first, I want to print this specify %c. So this will print the \x, I think 7f. So when I say \x, it is going to be hexadecimal again. So I'm going to try to control the bits, and I'm trying to produce the number 127, right? So the other thing is I want C as a integer. All right. So I want C as an integer. So I'm going to produce here %d. And then I'm going to show that actually I can add values to it. Right, so C plus 1 equals, and I'm going to have again %d, right? And we're going to print C, then C again. Then I'm going to add 1, but I want a 1 that is a character. So I'm going to say C plus \x 1. So it's hexadecimal 1, which is also decimal 1. All right. So let's see what happens now. Oh, and we get conversions into into int again, which is so stupid. This is not the GCC that I used to know, unfortunately. So I want this guy to be yes. Very good. Okay, good, right? So there's nothing printed here, right? Unfortunately. So this is because whatever code this is an invisible character. All right. So I'm going to repeat the experiment, and but before I repeat the experiment, I'm going to try to put a visible character there. Look at the value that we get here, right? So 7f is 2 to the power of 7 minus 1. So that's 128 minus 1, right? 127. Now we only have 8 bits. This is a character, and this is the old school character from the old days, because currently, since in this millennium, right, characters have become Unicode, right, and they take more than just 8 bits, right. But in the previous millennium, characters were limited to 8 bits, right? And then all sorts of people had made all sorts of artifices to add new characters and various fonts and so on, right? But the standard character was called ASCII and had only 7 bits, right? 128 values. So you can go and Google, and you'll notice that all the actually, let's do that now. All the characters that could be written from the keyboard. So we're looking for ASCII code. All right. I'm not sure why I went to Hawaii, but right. What you see here is the numeric codes in octal, which was the code used in those times. Let's find one. ASCII Wikipedia. Yeah, this is what I. All right. So let's see if we have a nicer table. Anyway, so all the characters that can be typed from the keyboard, right? They fit into this into 7 bits, right? So 128 of them. That's enough. So there's 32 of them that are control characters, and if you remember, we have already used this one, \n, right? And if you remember C, we might have used \t. And then there's the printable ones. They start at the decimal value 32 and keep going up to 127. Oh, 127 is not printed. Okay, so we picked the wrong one. So we're going to go to 126. Now, this set of characters is definitely insufficient because you want to have Chinese characters, you want to have diacritics on all the European alphabets, right? Most of them have letters with diacritics. you want to have, Hebrew or Arabic, Indian languages, all of them have to fit into the fonts, right? And this is why the set of characters has evolved, and it is into a standard that is nowadays called Unicode, right? But C is still old school and has not really evolved. So we're going to work with this set of characters and with these codes. Now, I was saying that these characters are actually numbers. It's these numbers that you can see here, right? So I just produced 127, 7F, which is not printable. I'm going to go back to 126, and I'm going to produce either of these two characters, depending on the font at hand. All right, and guess what? Printf can interpret the character either as a number, this number, when I use %d, or it can interpret it as the character with that code when I use %c. Okay, and this is what I was trying to show you. So let's actually have that experience. Put here 7e, which is actually a printable character, and instead of adding just 1, I'm going to add 2 to create the overflow again. Okay, so you see this character being printed here. So whenever I use %c, it will take this value and interpret it as printable character and give me the printable character for this. When I interpret it as integer, I'm going to get the integer value, right? But it is actually an integer because I can add 1 to it or 2 anytime I want. The important thing to remember is that whenever I add two numbers, they have to be of the same size. If they're not of the same size, the one that has lesser range gets converted to the wider range. And then we lose this property. And we see now that there are conversions that are performed on the fly. So this short, we encountered a problem with it. This should be F here. Okay, so is this clear? Everything is pretty much an integer, right? And everything has bits. And actually, there's another experiment that I want to do, right? Obviously, we can create unsigned characters, right? So I can have the same thing. And this is another thing that I was talking about. That there was another thing that I wanted you to understand. But let's say unsigned. So notice that only int is redundant. So I can delete the int from here, for instance, and I can delete it from here. Okay, doesn't matter. But the char here, I have to have it. So fg, right? This would be g, and I'm giving it the same value, right? And I'm going to have g and g and g. So now because we have unsigned, we don't have an overflow anymore, right? 127 plus 126 plus 2 is 128, which is now a legal value, right? Because our range for 8 bits goes from 0 to 2 to the power of 8 minus 1, which is 255, right? 256 minus 1 is 255, right? So now we're not going to see the overflow here anymore. Oh, that's not good. Actually, we didn't see the overflow here either. So I want this to be on sign char. So this should be char. I should see overflow. And then here, I should see no overflow. All right, so notice the overflow here. 126 plus 2, again, we're adding 2 actually. So plus 2 gives me minus 128, right? So 126 plus 2 would normally be 128, but that's already out of range. So we cycle, we wrap around to the other end of the range, and that's where we encounter minus 128, and that's the result. Okay, and similarly here. So this is an important limitation of, it's not a limitation of C, it's a limitation of number representations inside CPUs, okay, that we have to keep in mind. All right, now I'm going to replicate. So here we used unsigned, right? So unsigned, 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 right? I'm going to copy this line, and I'm going to use %d everywhere. What do you think is going to happen? Okay, so let's pay attention. This is the unsigned, and this is the signed, right? So it didn't matter that we have placed the unsigned here, right? The conversion to the screen was performed according to the specifier, right? So if the type and the specifier are not in sync, you will still get representation errors. All right, and essentially, whenever you look at what does the conversion mean? If the size is the same, it means nothing, right? So if I use an unsigned and then a signed int is of the same size, what's going to happen when a conversion is needed? Nothing. The bits are copied from one side to the other, unchanged, right? It's just a matter of convention. It's in the eyes of the beholder whether the number is positive or is unsigned or signed. And where is the eye of the beholder? Here is the eye of the beholder. So this is ultimately where it counts, whether we consider the number to be signed or unsigned, right? However, whenever we convert a number from between different sizes, right? What's going to happen with the bits? Well, if it's smaller size, we're going to truncate. How we're going to truncate? We're going to remove the higher order bits. So if I want to go from 32 bits to 16 bits, I'm going to remove the higher order 32 bits. So it's like taking modulo 2 to the power 16. Okay? That's the actual operation. So remember, modulo 2 to the power 16. Okay? What if I have to expand? What if I have a 16-bit number, and I need to expand it to 32? So this is where it's interesting. If I have a signed conversion, then, so as I go, obviously I have more bits than I need, right? I have the 16. And I have to copy into 32. So where am I going to copy the 16? Into the lower part of the 32, right? Then what am I going to fill the upper part? Louder. With the? So it depends. If the conversion is unsigned, I'm just going to fill with zeros, right? If the conversion is signed, I'm just going to replicate the higher order bit of the 16, right? Because the higher order bit actually tells me whether it's positive or negative. Whenever the higher bit is 1, I have a negative number, right? If you look here, right? Whenever the highest bit is 1, the highest rank bit is 1, I have a negative number, right? Mm-hmm. So if I'm going to expand it to a bigger number, if I want to have a signed conversion, I'm going to replicate that bit, right, into all the 16. So that's something we can easily check, right? So if I have unsigned x equals 0 initially, right? And then I have unsigned int. And then I have short. And so this would be signed y, which would be equal to -1. And now I'm going to say x equals y. Y equals %. So %u, right, because it's unsigned, \n. So what's the value of y, do you think? So this would be an unsigned conversion. X is unsigned. Sorry, you. I should say y here as well, right? Okay. So that's the value. But actually, this should not be the value. This should be, I should get, really, I have to do this all the time, right? I should be getting 32,767 if I say unsigned short. No. I have no idea why. It tends to work better with char. So let's say char is -1. Oh, we're looking at y. Why are we looking at y? We should be looking at x. Sorry. So we want here to say x and x, right? So I want to see the value that x got. Oh, and no progress. Is this the reason? No. Let's say unsigned. Okay, fine. So this is the answer I wanted to get at. Though the implicit conversion to int. So nowadays it seems that everything is converted to int. I'm going to redo this experiment by using char. I think char doesn't suffer from these conversions. No, this stays unsigned, and then this should be char, and I want it to be minus 1, and then x is assigned y. No, still doesn't work. Okay, so in order to have a conversion, I need to do it explicitly. There's no implicit conversion. So there's the implicit conversion is always to int. All right. So this is what is important here. So char minus 1, right? This has 8 bits, right? So when I say char minus 1, 8 bits of minus 1, what is that value? It's 0xff, right? So it all bits equals to 1, right? And then I convert this into 32 bits. And this is an unsigned conversion, right? So what's going to happen? I'm going to have 24 bits of zeros. So 0x0. So 0x0. 24 bits of zeros, that's 6 zeros, right? And ff. So this is an unsigned conversion. Essentially, these bits have been copied into the lower part of the bigger number, and then the rest has been padded with zeros, right? On the other hand, okay, let's say that I have int z equals 0, and then I perform z equals char, but actually this is already char, z equals y, right? And this will give me the value z equals percent d this time, backslash n, and we're printing z, and this will give me minus 1. Yeah, semicolon here. All right, so z is now minus 1. So what happens here in this one is that 0xff, right? So this gets copied. So I'm going to have 0x, and somewhere here I'm going to have the ff, right? And then if you look at the first bit here, the first bit is 1 because it's a negative number, right? The first bit is 1. And that bit of 1 is replicated for this entire stretch, right? So this will produce FFFF, right? So we're going to have 6 Fs. And this is going to be minus 1 on 32 bits. So we have a sign conversion. Okay? Anyway, so this is just to make you aware. These are very nitty-gritty and to make you aware of the fact that these things exist, right? C is a complicated language because of that. It's not conceptually very difficult, and if you're going to try to think through every of these situations, right, you're going to find the right conversion and the right result, right? Every operation in itself is relatively easy, right? The problem is that when you in like 10 lines of code, you can have 7, 8, or maybe even more such conversions going on in one go, right? It's not simultaneous, but it's one go. It's on the same page. It's 7 or 8 places where you have to be aware of these things, and it becomes just too difficult, right? This is why C is a complicated, dangerous language, if you will, right? It is shunned by application developers. Yet this kind of operations, this kind of conversions are necessary in embedded systems, in operating systems, in writing drivers, right, for hardware that you're adding to your system, right? And you can't live without them at that level, right? So C is the adequate language for that level. You won't get any homework that will specifically test you on this, all right? But next time, what I would like to do is go through a few pieces of code that are traps, typical traps that are resulting from this. So, for instance, right, if we have G is a character, right? So if I say something like G is assigned 0, and then while G less than 128, do something. I'm not going to say that right now. And then I'm going to say G++. Will this loop ever terminate? Will you ever exit the loop? Just 2 minutes. Yeah, the answer is no, right? Because the range for G, which is a character, remember, char. Oh, this is an unsigned char. Let's make it F. Sorry, signed char. Yeah. So the range for a character, if it's signed, is what? So it's 8 bits. It's signed, so it's going to be minus 2 to the power 8 minus 1, right? Up to 2 to the power 8 minus 1 minus 1, right? So if I have n bits, replace 8 by n, you're going to get the range for a signed integer, right? So this number, if you look carefully, is 127, right? So if I say, while f less than 128, right, it will always be less than 128. What happens when f reaches 127? It reaches 127, we do f++, and what's the next value? Minus 128, very good, right? So this loop never terminates, right? And you can run into a lot of tricky code because of that, and you can run into bugs that are very difficult to discover, right? Yeah. So this is just one aspect, and I'm going to have another such lesson on pointers and show you how pointers can be very very dangerous, right? With great power comes great responsibility. This is one of those situations, right? So therefore, C as a language should only be used where other languages cannot do the job, really, right? Because this aspect of C makes it extremely dangerous, really, and code written in C becomes very difficult to maintain, right? Tends to be very bug prone. So that's it for today. We're going to keep looking at the structure of data, all these data types. So we're going to look a little bit at doubles. And I want to do all the arithmetic operations emphasizing bit operations, right? So I want you to understand exactly that numbers are made of bits. Okay? Cool. If you have any questions, feel free to stick around and ask. Otherwise, class dismissed. Thanks for coming.